Hello, my name is Tina Grotzer, and I'm a faculty member and a researcher at the Harvard Graduate School of Education. Recently, I spoke with a reporter at the Times of India, and she wrote a lovely piece on the role of the teacher in developing environmental awareness for students. By chance, Dr. Sheena happened to read that piece, and through a bit of destiny, she brought us together today so that I am able to speak with you. It is my pleasure to be able to address your conference, and I hope that at some point I'll be able to come and visit to learn more about the work that all of you are doing. My work for the past number of decades has focused on helping the next generation to become more eco-centric global citizens, so really educating for the planet. We know that global climate change is upon us. We see it around us. We see it affecting the lives of those around us and all around the world. We also know that green jobs and becoming global citizens requires being able to think about these kinds of issues and to be able to think in a way that involves systems thinking and the ability to deal with complexity. And we see that across the various inventories having to do with green jobs. So this one here from the World Economic Forum highlights both system skills and complex problem-solving skills. But the research shows, and the research that I've been doing for many years along with some of my colleagues, that human cognitive architecture is not well adapted for reasoning about complexity. Not only for reasoning about it, but also perceiving and being able to attend to it and then following through. So what's going on there? Well, we know that complexity is hard to reason about for a number of reasons. There's a lot of cognitive load. It has dynamic aspects. There are different levels of explanation that are interacting. They have interacting parts. And there's sometimes a differentiation between both the function and the structure of a system. But the special case of causal complexity is where I have focused my work for the past 3 or 4 decades. So when reasoning about causality, we tend to sum across our experiences and we seek out patterns or correlations between various events. That makes sense. Sometimes we oversubscribe or prescribe causality. We also seek out plausible mechanisms, what makes something happen, and we may intervene on a pattern to see what's making it happen. However, we also tend towards efficiency. As human beings, our attention gets pulled elsewhere, and so we notice the patterns that are closest to us, and we notice the variables that are closest to us. Patterns that are meaningful or familiar are more salient to us, so we're more likely to notice them, and we default towards familiar or well-traveled patterns. And the neuronal synapses, the synaptic pathways in our brains are formed in a way that underlies that finding. So what are some of the implications for the types of patterns that we notice or miss? There are a number of simplifying default assumptions that we engage in. This is a list of them from the research. I'm not going to speak about all of these today. I'm going to highlight a few of them, but I have written about them extensively in a book called Learning Causality in a Complex World, Understandings of Consequence. And in this book, I review the research related to each of them. So humans find it very difficult to reason about things like extended indirect effects, feedback loops, time delays, emergence, distributed causality, non-obvious causes. These are all very much a part of what's going on in the world of climate change. So let's look at a few examples. So when I was a kid, there was a big focus on pollution and air pollution, and there still is in many cities today. Air pollution is very different than carbon. You can see air pollution. It brings it to your attention regularly, and it makes it easier to reason about. It's very difficult to attend to what we can't see, and mechanisms that are non-obvious escape our attention. We don't allow for causeless effects as human beings, But until we can see effects, we often don't look for causes. And that gets us in trouble in a system such as climate change, where once you have discernible effects that you can see, it may be too late due to tipping points. We also tend to think about intentionality when it comes to causes, and to weigh what we see as intentional causes more heavily. In the US, 9/11, people focused a lot of attention because it was an act that was of terrorism that was intentional, and it really galvanized people to act. And we see when someone does something on accident, we tend to think it's not as causal, even if the outcomes are just as bad. But we're more likely to galvanize when we think it's an intentional act. And that's really problematic for climate change research, because the consequences are more catastrophic, more extended. They're across the entire planet, but it makes it harder to act when the outcome is unintended. We really care about agency, and we care about the meanings behind agentive actions. So Lake Nyos is a lake in Cameroon, and one morning in the 1980s, thousands of people died around the shores of Lake Nyos, and they died because it's in a volcanically active region, and gases spewed up all at the same time. There was lake overturn, and it displaced the breathable oxygen around the lake. However, when this happened, and people suffocated and they died, it was very sad. But when it happened, people looked for intentional agents. They looked for acts of terrorism. They looked for who had done this to them first. It was very hard to think about the layers of the atmosphere and this non-obvious cause, the gases rising up that they couldn't see, as being the cause of such a catastrophic event. Distributed causality is also very hard for us to think about. When actors are spread out all over, it's very hard for us to think about the collectivity of their efforts or their behaviors or their actions, and how they come together for an emergent outcome that is much bigger than the sum of its parts. There are a lot of examples of distributed causality. It can be both a positive force, if we're gathering together to do good. It can also be unintentionally negative, such as all of those cars not really thinking about the collective outcome of their actions. So research shows that students tend to use more distributed causal reasoning than earlier research suggested, and they were also somewhat flexible, going between distributed and more centralized causality, but it was very hard for them to reason about synergistic or emergent effects, and very few students did. One of the forms of causality that we've looked at is spatial complexity, and we call this action at an attentional distance. There's a lot of research and development on action at a distance when two things are separated in space and time, but when you have action at an attentional distance, it's actually in a different attentional frame. So in the traditional developmental studies, kids are given things like magnets, and they see that they're not touching, but both of them move together, so they see the correlational impact. With action at an attentional distance, you have the cars in one frame, and you may have the melting Arctic ice in a different frame. So people have a harder time connecting them. Same thing, the Marshall Islands are far from many of us, so we don't think about what's happening there, and we don't connect it to our actions here. That's why I love things like this that sort of bring the two pieces together. This is on the street in Cambridge, and it basically says, you might not be thinking about what's far away from us, but you should. This is a really clever commercial by Nissan, suggesting that if you buy a Nissan Leaf, you're thinking about the polar bear every day. In this commercial, a polar bear takes a walk down from the Arctic, and he comes to this neighborhood, and you think he's going to eat this fellow, but actually gives him a hug. So we know that students focus on more local effects than distant ones. They often use domino-like causality to figure out when there's distant effects, and that helps them to give more extended explanations. The kids who are able to think about distal effects are often the ones who understand mechanisms. So in teaching science, that becomes important. It becomes really important that they understand the underlying causal mechanisms and how they behave to help them make a connection between local causes and distal effects, or vice versa. So all of this research suggests that it's really important to help learners understand the implicit causal assumptions that they're making and to be sensitive to occasions when they need to revise them. They need to understand there are different types of causal patterns and features and learn how to think about them. They need to understand the underlying causal mechanisms such as carbon, so that they know how to explain the covariation patterns, and to even know that they exist, because if you don't think to look for them because they're in different frames, you won't. And I would add that there are ways of knowing from different cultures around the world that do adopt more complex ways of thinking about Earth's dynamics, and we need to learn from those cultures. So I'm going to show you just a couple of things that we've done to revise the way that students think about their underlying causal patterns. We do an activity that in the classroom called recast activities, and we start with this question about what's going on when something sinks or floats. And kids will say it's about the object and how heavy it is. So a lighter object will float and a heavier one will sink. Then we give them what we call a recast activity, which is designed to reveal the underlying causal structure so that they can shift the way they think about what's going on there. So we first show them two beakers, and we put two pieces of candle in from the same larger candle, and they see the small one is floating and the bigger one sinks, and they say, yes, that's exactly what we think should happen. Then we swap the candles, and they say we've tricked them. And they'll say that because when they see the bigger one floating and the smaller one sinking, they suddenly are paying attention to what's in those beakers. And they say, well, what did you do to the water? And here they're shifting their understanding from a simple linear, this makes that happen, to a relationship. It's a relationship between the density of the liquid and the density of the object. Same thing for layers of the atmosphere, as I explained earlier in our example from Lake Nyos. So it's a relational causality, and it's a different way of thinking about things. But so often in schools, we reinforce the simpler notions, floaters and sinkers attached to the object. It reinforces a simple linear notion, and that's not helpful when you want a relational causality at the core. Sinking and floating is essential to many understandings, and it relates to convection currents and many of the understandings related to climate and climate change. So our recast work told us that, kids made these simplifying assumptions, and that if you designed instruction that helped them to restructure their causal assumptions, it mattered for all of the kids. It mattered the most for the ones who struggled in learning. So the lower level achievers made the most dramatic gains. And we also saw that kids were able to transfer these causal concepts to many other science concepts, particularly when they had support, metacognitive support. We have a website that has lots of curriculum on it that uses this approach, and that you are welcome to download resources from. One other thing that we did is we were looking at distributed causality, and we thought, how can we teach that in terms of climate change? So we developed a whole unit, a whole curriculum module, specifically focused on distributed causality, and there's also one on spatially distant causes. One last thing that we did is we developed, or we're still doing, we're developing virtual worlds. And these virtual worlds have at their core a very complex scenario of some type. And students go into these worlds and they explore. There's substantial supporting structure to help them see things that they otherwise might miss, graphical representations to help them reason about what's going on. And they go into these worlds and they are playing with the complex causal dynamics involved and learning a lot about causal complexity as it relates to planet Earth and the environment. So in this particular case, they have to reason about spatial gaps between causes and effects to figure out what's going on at a local pond. There's also non-obvious causes that they can zoom in on, and they can time travel in this one. So they can go back and forth in time to observe subtle changes that they otherwise would have missed. So there is some experimentation in the world, the kind that scientists use, and we also have a number of thinking moves that we introduce them to as part of understanding the epistemic lenses, or the disciplinary knowledge that ecosystem scientists engage in order to construct complex causal explanations. So, in summary, becoming a global citizen requires thinking about complex causality in systems. The human mind works in these ways that make it really hard to think about complexity. So students need opportunity to learn how complex causality works, and that our default assumptions can be problematic, and well-designed instruction can help them to get there. It can help them to become better complex causal and systems thinkers and to grow into global citizens. So we have a lot of resources available. One of our websites is called Cognition in a Complex World, and you will find some of our curriculum materials there. We also have a series of curriculum for the virtual world experiment that I demonstrated, and that's on our EcoLearn website. There are also publications that support the sort of summarizing statements that I've been making, and I'm glad to share any other information related to these studies with you. So it was a pleasure talking with you today. I wish you the very best in your conference and hope that we get to meet and exchange ideas soon. Thank you very much.